All right, folks, let's go ahead and get started with 3.9. So 3.9 is a section called derivatives of exponential and logarithmic functions. And so let's start with what we know, okay? So what do we know? We know that derivatives are rates of change. And maybe specifically, we think about it as the instantaneous rate of change of a function. Now, we could use the formal definition of the derivative. We can always use that. But because that's kind of time consuming, we've started a collection of tools we can use to make that shorter. Specifically, we've looked at power rule, constant rule, the linear rule, sum and difference rule, the product rule, the quotient rule. And in the last video, we learned about trig derivatives. And so we added 6 new rules to our toolkit. Now, what's new, we're going to be looking at derivative rules for exponential and log functions, okay? And so we're going to learn a few more rules here. And it's really important that we remember as we're learning rules, we're constantly asking ourselves, when do we use what? Not just how to use it. That's an important question, okay? So we want to still think about how we use rules, but more specifically, we want to think about how we know when to use those rules, okay? So let's get started with the derivatives of general functions, or general and natural exponential functions, okay? So before we talk about that, remember we talked about the power rule, and I even included like a whole paragraph about it where it says that, here's our rule, we bring the power down and we take one away from the power, but only when n is a number, okay? And so what that meant for us at the time was that the power rule works when we have a variable to an exponent of a number, okay? Now, at the time, I was like, this is important, but I think we probably spent more time practicing how to use the rule. And so what's going to be a little bit different for us now is we're going to talk about what happens when those conditions are reversed, okay? But before we get there, let's do example 1 and 2 just to kind of practice a little bit. The derivative of x squared, well, we have a variable in the base and we have a number in the exponent. So we can use the power rule and we'll get 2x to the 2 minus 1 or just 2x. And let's see, the second example sure does look like I have a number in the exponent and a variable in the base. So again, I can use power rule. So I'm going to bring that 1/2 down, x to the 1/2 minus 1, which should give us 1/2 x to the negative 1/2, which we typically see as 1/2 square root of x. Okay. And so those are 2 kind of quick examples that remind us, yes, we know the power rule. We know it works with positive exponents and it also works with fractional exponents. But as we already color coded, the base has to be a variable and the exponent is a number, okay? Now, in the case when the conditions are reversed, we need a new rule, okay? And that is so, so important that when we reverse the conditions, we're gonna need a new rule. And what I mean by that is now we have a number, wow, a number to a variable, all right? So our base is a number now. It's not a variable. And our exponent is the variable, okay? And so here are two rules for when we have that to be true. So this case is the natural exponential function, okay? E to the x. This one is one of probably students' all-time favorite because the derivative of e to the x is e to the x. That's pretty cool and pretty special, okay? Now, what happens if you have a base that is not e? You'll have to compensate for that by multiplying by natural log of that base, okay? So this second case is when the base is not e. Okay. So let's practice using these rules. All right, so the derivative of 2 to the x. Well, that means I'm going to use the a to the x rule, right? I'm going to go ahead and use this one because my base is 2, it is not e. All right, so the rule says that it's going to be a to the x natural log a. If we fill that in, we'll get 2 to the x natural log 2, and that, my folks, is the derivative. Okay. Now, if we pop over to example 4, this one is our natural exponent. The derivative is just going to be e to the x. Looks like there's a little bit of a lag, so I'll kind of wait for that to catch up. There we go. All right, so the derivative of e to the x is e to the x, okay? Now let's do a couple problems where we include these with some other types of functions, okay? All right. So I want to find y prime if y equals 2x to the 5th times e to the x. Now right here, I should be clued in that I'm going to need product rule, right? 2x to the 5th times e to the x means I need to have the product rule. Let's set up our product rule. Okay. U equals 2x to the 5th. And v equals e to the x. And du is going to be 10x to the 4th, and dv is going to equal e to the x. Okay. I don't know why there's a little bit of a lag here, so just be patient, please. Maybe I'm saying that to myself because it's frustrating for me, but I appreciate your patience. All right. So now let's go ahead and find our y prime. I'm going to plug everything into the product rule, which is u dv plus v du. And we're just going to plug in what we have, which will give us 2x to the 5th times e to the x plus e to the x times 10x to the 4th. Okay. And when we clean this up, I do notice that we have a common factor of e to the x and e to the x. So I'm going to go ahead and factor out that e to the x. So I'm going to get e to the x. And in parentheses, I have 2x to the 5th plus 10x to the 4th. And I notice that I can even factor that out a little bit more. I'm going to take out the greatest common factor, which is going to give me 2x to the 4th e to the x times, let's see what's left, x plus 5. That, my folks, would be the derivative of 2x to the 5th times e to the x. Okay. All right. Let's take a look at example 6. Find y prime if y equals sine x 3 to the x. Well, looks like I've got a division going here. So I'm going to go ahead and make note that I should use the quotient rule to figure out this derivative. So we're going to go ahead and set that up. U equals sine x, v equals 3 to the x. That means du equals cosine x and dv equals 3 to the x natural log 3. So I got to remember that natural log of 3, especially when that base is not equal to e. Okay. Let's find our y prime. Plug that into the quotient rule, v du minus u dv over v squared. That is going to give us 3 to the x times cosine x minus sine x times 3 to the x natural log 3 all over 3 to the x squared. Okay. Now, this next part, I think being able to see this next part comes with a little bit of practice, but we might notice that there's a 3 to the x in the front in the first term. We might notice there's a 3 to the x in the second term, and we might notice that there's actually 2 3 to the x's on the bottom. And so I'm going to go ahead and reduce everything by dividing out a 3 to the x, which should give me, I'm going to write it down here, cosine x minus sine x 3 to the x over, sorry, not 3 to the x, natural log 3 over 3 to the x. Okay, so we just divided out that common factor in the numerator as well as the denominator. All right, I hope it's not too annoying to be watching with this with the lag. My apologies. All right, let's take a look at example 7 here. So if a of t equals 1000 e to the t, describe the mosquito population after t days. All right, so we have this function that tells us how many mosquitoes we be having after t days. What is the rate of change of a of t after 4 days? So when I see this rate of change of a of t, I'm automatically thinking a prime of t. Okay, so that part right there means a prime of t. And after I find a prime of t, guess what number I'm going to plug in? I'm going to plug in 4 for the number of days. Okay. So let's, number 1, find a prime of t. And so that's just going to be a prime of t. Let's see, constant multiple. So constant is 1000 and derivative of e to the t is e to the t. All right, step 2, we're going to sub in t equals 4. And so we'll get a prime of 4 equals 1000 e to the 4. We'll just leave it as 1000 e to the 4, and that is going to be mosquitoes per day. Okay, there's a lot of mosquitoes growing in population. That many mosquitoes per day. That's kind of gross. You. All right, but that's kind of how we can use the ideas of rate of change that we've already seen and a new kind of function, the exponential function, but still tie it into derivative. Okay. All right. What do we have next? We have derivatives of general and natural logarithmic functions. Okay. And so I put these two rules for you right here. Derivative of the natural log of x equals 1 over x. That's the more simple case. All right, so this is when the base is e. And the derivative when the base is not e. So base is not e is 1 over x times the natural log of a. All right, so that natural log of a kind of compensates for the fact that that base is not e. Okay. All right, let's do a few examples on this. All right, so derivative of -4 log x. Well, this is our constant multiple rule. So we're going to get -4 times the derivative of log x, which is 1 over x, natural log of, what is the base here? Okay. Now, this is also known as the common log, right? It's so common that we don't write the base, but it's secretly log base 10 of x. So that means the thing that I'm doing natural log of a is going to be natural log of 10 in this case. All right. What about example 9? Derivative of natural log x over 3. Well, this is actually the same thing as saying derivative of 1/3 times natural log x, which when we have the constants, we can pull them right out to the front. 1/3 times the derivative of natural log of x. Okay, that's actually a pretty important concept here, which we kind of saw when we did the other quotient rules where we could simplify first. All right. But now we know the derivative of natural log is just 1 over x. So I'm going to get 1 over 3 times 1 over x, which is going to give me 1 over 3x. All right, let's try a few more examples to finish off 3.9. All right, example 10. Wait for that screen to move. We know we're dealing with a lag today, but at least I can share my screen, so I'll take that. All right, number 10. Find y prime if y equals cosine x times natural log x. Right away, we should be recognizing we are using the product rule here. Okay, and I'm going to go ahead and set that up. U equals cosine x, v equals natural log x, and I got to remember the rules. Du is negative sine x, dv is 1 over x. And once I've got all those, we'll go ahead and find our y prime using the quotient rule, or sorry, the product rule, which is u dv plus v du. And I'll get cosine x times 1 over x plus natural log x times negative sine x. And let's clean that up a little bit. We'll get cosine x over x minus natural log x sine x. That is the y prime for the y of cosine x times natural log x, okay? So for better or for worse, I think the more we do of these, the more we realize that that underlying structure is pretty much the same, but what's different is we just have a bunch of rules to choose from, okay? All right. What rules should we be thinking for finding y prime if y equals log base 3 of x divided by tangent x? Well, we should be thinking quotient rule. Okay, so let's set that up. U equals log base 3 of x, v equals tangent x. All right, that gives us du equals 1 over x times natural log 3, and dv equals secant squared x. All right, y prime is going to equal v du minus u dv over v squared. And then I'm going to plug everything I found into there. So tangent x times 1 over x natural log 3 minus log base 3 of x times secant squared x all over tangent squared x. And probably the only thing I would expect you to simplify here is turning this first two terms into tangent x over x natural log 3. And then we can just subtract the rest and divide it by my tangent squared and call that a day. Okay. I think a lot of times what makes these tricky is like convincing ourselves that we are good enough mathematicians to be looking at things that have so many different types of letters and that it's okay and that we've earned the point of being here, okay? So yeah, this is a lot of plugging things in, but I bet if you just pull from the rules and follow those rules, it's not too bad. Okay, I wouldn't worry too much about how do we simplify things. I would worry more, okay, did I get the right rule? Did I do the quotient properly? Did I get my u and my du, my v and my dv? Those are probably the more important pieces, okay? So we're going to finish off this section with finding the equation of a tangent line. Okay, so let's go ahead and take a look at example number 12. Find the equation of the line tangent to y equals 2 ln x at x equals e. All right, so let's go ahead and start off by writing the equation y minus y1 equals m parentheses x minus x1. And we know from earlier that we're going to need our x1, which is given. We're going to need our y1, which we use the function to find. And then we need an m, which we're going to get from the derivative. Okay, so the orange x is given. The green y, we have to do a little bit of work, but then that blue m, we probably have to do the most work. That's where we need our derivative. Okay. So let's find our y1. So y of e gives you 2 times natural log of e. Natural log of e, well, that is 1. That's a nice value to know, okay? A lot of times folks will ask you to simplify things, but it's not simplifying like we just saw in example 11. It's simplifying like this, where we know the natural log of e is 1. That means that our y1 is just 2. Okay. All right. Step 3, find y prime. All right. Y prime is going to be 2 times the natural log of x has a derivative of 1 over x, which means that's 2 over x. And I'm going to find y prime of e to be my slope, which will be 2 over e. So slope is 2 divided by e. That is the same thing as the derivative at e. All right, so slope is the same as 2 over e, which is the same as that first derivative, and then we plug in e. Okay. We've got all the pieces we need. So we're going to sub in all values. And we'll get y minus 2 equals 2 over e parentheses x minus e. And we can go ahead and leave it just like that. Okay. So y minus 2 equals 2 over e parentheses x minus e. And leave it in that form. Please don't simplify. You're totally good to go here. Okay. All right, folks, I apologize for the lag in this video. I hope it's not too annoying. But if you have any questions, stop by tutoring or stop by office hours, and I'm more than happy to help you out, okay? All right, see you folks on Wednesday.